The cosmic fine-tuning paradox confronts us with a single disquieting fact. The fundamental constants of physics appear calibrated with extraordinary precision, and even the slightest deviation would erase the possibility of atoms, stars, chemistry, or life. This is not an aesthetic coincidence. It is a quantitative knife edge on which existence balances. You stand inside a universe whose scaffolding behaves as though it were adjusted before anything physical could begin. Begin with the strength of gravity. If it were weaker by a few parts in 1036, matter would never condense into stars. If stronger, stars would burn too quickly for complex structures to evolve. Consider the ratio between the masses of the electron and proton, alter it by a fraction of a percent, and stable molecules dissolve into impossibility. Even the cosmological constant, the energy density of empty space, sits within an unimaginably narrow range. Push it slightly higher, and cosmic expansion outruns the formation of galaxies. Push it lower, and the universe collapses before it can think. Each number seems independent, yet each supports the same fragile outcome. A world capable of noticing the numbers. The strangeness is that physics works only because physics could have failed. Scientists call this fine-tuning, not to imply intention, but to describe the improbable alignment of parameters that make coherence possible. The paradox arises because natural explanations should tolerate variation, while this universe behaves as though variation were forbidden. It suggests that either we misunderstand probability, or we misunderstand the underlying physical laws, or reality holds more layers than the observable slice we inhabit. Each path reshapes what normal means. The unsettling realization is simple. Before we debate why life exists, we must confront the deeper mystery that the universe first arranged the conditions that allow anything to exist at all. Fine-tuning becomes clearer when we quantify how unforgiving the universe is to deviation. Each physical constant defines the structure of reality, but these structures do not respond gently to change. They snap. The gravitational constant, the charge of the electron, the strength of the strong nuclear force. Each one lies within a range so tight that shifting it by even one part in 1040 unravels the cosmic script. This precision is not aesthetic. It dictates which universes can ignite and which collapse into sterile symmetry. The numbers behave less like suggestions and more like boundary conditions for existence itself. Look at the strong nuclear force, responsible for binding protons and neutrons in atomic nuclei. Make it slightly weaker, and hydrogen becomes the only stable element. Make it stronger, and almost everything fuses immediately into heavy nuclei. Either way, the chemical variety that life depends on disappears. This sensitivity means that chemistry, biology, and thought are not inevitable outcomes of matter. They are consequences of an unusually permissive configuration that could easily have failed. Life is not riding a wave, it is clinging to a ledge, and that ledge is unimaginably thin. Astrophysics deepens the puzzle. The balance between gravity and fusion inside stars rests on constants interacting with near-perfect proportion. A star shines only because competing forces tie in a narrow equilibrium. Collapse pushes inward, radiation pushes outward. Upset this balance and stars either never ignite or burn as brief, furious flares unable to seed planets with heavy elements. What seems like ordinary starlight is actually the product of a cosmic compromise that barely holds. The twist is that fine-tuning doesn't merely make life possible, it makes our kind of universe possible. Change the constants, and you don't get a different version of reality. You get no coherent reality at all. Fine-tuning becomes paradoxical not because the constants are precise, but because they appear too precise for chance to be a reasonable explanation. In physics, improbability is tolerated when large sample sizes rescue statistics. But fundamental constants do not arise from repeated trials. They arise once at the birth of a universe. The moment you treat them as random values drawn from an unknown distribution, the probability of landing on this exact combination collapses to numbers so small they stop functioning as probability at all. A universe capable of stable atoms occupies a vanishingly thin region in parameter space. And yet this is where we find ourselves. You're looking at a dart thrown into darkness that somehow landed on the only point that matters. Imagine varying the cosmological constant, the most fine-tuned parameter we've ever measured. Its allowed range for a universe with galaxies is roughly 1 part in 10^120. That is not small, that is indistinguishable from zero. A constant so delicately balanced that it makes lotteries look deterministic. Treat this number as a random draw, and the existence of stars becomes more improbable than picking one specific atom out of the entire observable universe. What this suggests is that probability, as we use it in daily intuition, cannot bear the weight we place on it here. The universe behaves as though this number had no freedom to drift. This collapse of probability forces a deeper shift. If chance cannot plausibly select the constants, then something about reality constrains them. Not in a purposeful sense, but in a structural one. A universe that permits complexity may be far less permissive than we imagined. It may be that the laws of physics are not choices but consequences, that the constants feel adjustable only because we do not yet see the mechanism that locks them in place. The paradox sharpens here. The universe looks random in its events, yet looks anything but random in its foundations. The search for what fixes the constants begins with the assumption that they are free parameters, but modern physics quietly undermines that idea. Every successful theory in physics reduces apparent complexity by revealing deeper symmetries, mathematical rules that determine how forces and particles behave. If the constants emerge from such symmetries, then they are not dial settings, but byproducts of a deeper structure we haven't yet uncovered. This shifts the perspective entirely. Instead of asking why the constants are just right, we ask why the underlying architecture allows only values that produce coherence. The twist is that the constants might not be tuned at all. They might be the only possible outcomes of a universe that can exist consistently. Consider the way quantum field theory generates particle masses. These masses come from interactions with the Higgs field, and although we treat the coupling strengths as independent parameters, symmetry principles sharply restrict their possible forms. In a similar way, string theory proposes that fundamental constants emerge from the geometry of extra dimensions, each number reflecting the curvature and size of spaces we cannot directly observe. Change the geometry and the constants shift, yet not arbitrarily, only within patterns defined by the theory's internal logic. If such a framework is correct, then fine-tuning is less a coincidence and more a sign that physical law sits on a razor-thin set of self-consistent solutions. What looks like fragility may be structural inevitability. This interpretation reshapes the paradox. It suggests the universe is not improbably balanced, but mathematically compelled to be the way it is, as though self-consistency selects the constants long before matter appears. In that view, we are not lucky observers inside a fortunate cosmos. We are observers in the only cosmos that doesn't contradict itself. The shock emerges from realizing that the universe may be precise not because it favors life, but because precision is the only state in which a universe can exist at all. The multiverse enters the discussion not as fantasy, but as a mathematical consequence of several leading theories, offering a statistical way out of the fine-tuning paradox. If countless universes exist, each with different constants, then our improbable set of values becomes less surprising. In a sufficiently large ensemble, even extremely rare combinations inevitably occur. The constants would no longer demand explanation through necessity, they would simply be the values compatible with observers emerging somewhere in the vast landscape. Yet this proposal replaces one mystery with another, a cosmos that explains our numbers by drowning them in infinity. The twist is that solving fine-tuning statistically requires a reality so large that it becomes physically unreachable. Inflationary cosmology provides the first hint of such multiplicity. During the early universe, quantum fluctuations in the inflation field could cause different regions of space to bubble off with distinct physical properties. Each bubble becomes a universe with its own constants, its own particle spectrum, its own notion of what can exist. String theory amplifies this idea by predicting a landscape of possible vacuum states, each one corresponding to a different set of physical laws. If both frameworks are correct, then fine-tuning resembles a selection effect. Observers find themselves only in regions where complexity is possible. This logic feels clean, but it introduces a conceptual fracture. We explain the precision of this universe by invoking a collection of universes we can never observe. The deeper issue is not the existence of other universes, but the role they play in making ours intelligible. Fine-tuning becomes less a feature of fundamental physics and more a filter on where conscious observers could arise. This reframes the paradox. Instead of asking why the constants fit life, we ask why life fits one narrow corner of an immense, unseen reality. The shock comes from recognizing that understanding this universe may require accepting countless others we can never touch. Anthropic reasoning claims that fine-tuning only seems mysterious because we're looking at the universe from the inside. Any universe incapable of supporting observers would, by definition, never be observed. This transforms the constants from cosmic curiosities into preconditions for perception itself. The argument feels tautological, yet it forces a crucial shift. The universe does not need to be probable, only compatible with beings capable of noticing improbability. The twist is that the act of observing the constants becomes entangled with the very fact that they permit observers. Consider the basic anthropic insight. We observe a universe where stars live long enough to forge heavy elements, where chemistry can explore combinatorial space, where stable structures persist across billions of years. But we observe it only because universes without these features cannot host observers. This creates a selection effect. We are not sampling all possible universes, we are sampling only the tiny fraction that allow the emergence of minds capable of sampling anything at all. The logic is sound, but it carries a quiet discomfort. It doesn't explain why the landscape of possible universes exists in the first place. The deeper tension appears when anthropic logic confronts probability. Fine-tuning doesn't vanish when we acknowledge selection effects, it simply shifts to a higher level. If constants are drawn from some distribution, then that distribution must itself make habitable universes possible, often enough for us to find ourselves in one. If the distribution heavily disfavors life-compatible constants, then even with a multiverse, the fact that we inhabit such a universe remains puzzling. The anthropic principle filters the outcome, but it cannot by itself justify the permissiveness of the underlying mechanism. This reveals an unexpected reversal. The anthropic lens doesn't solve the fine-tuning paradox, it sharpens it. By tying our existence to the structure of physical law, it forces us to confront how deeply the universe had to cooperate just for a question like this to be asked. Fine-tuning becomes even more striking when we examine how physical laws interact. Constants appear independent, yet their effects interlock with uncanny precision. The strength of electromagnetism determines how atoms hold together. The strength of gravity dictates how matter collapses into stars. Nuclear forces govern the synthesis of elements inside those stars. Change any one constant, and the others no longer cooperate, causing the entire physical structure to fail. This interdependence suggests that the constants might not be freely variable at all. Instead, they may be constrained by a deeper, unseen coherence that makes their values inevitable. The twist is that the paradox may come from mistaking a boundary condition for a choice. Models in theoretical physics hint at such constraints. Grand unified theories attempt to merge the strong, weak, and electromagnetic forces into a single framework, implying that the apparent constants we measure now are residues of a higher symmetry state that existed in the early universe. In such theories, the values we call tuned emerge naturally from how symmetry breaks as the universe cools. What looks like arbitrary precision may simply be the mathematical fingerprint of a larger order. The constants feel adjustable only because we're observing the final products rather than the generative rules that produce them. Quantum gravity research pushes further, proposing that spacetime itself may arise from more fundamental processes, networks, information, or discrete structures whose collective behavior produces continuous physics. If laws emerge from such substrates, then fine-tuning may reflect the self-consistency of the substrate rather than any improbable selection. The constants would then be features of the only stable solutions permitted by the underlying framework. This reframes the paradox once again. The fine-tuned cosmos might not be tailored for life, nor sampled from a vast statistical ensemble, but compelled by the minimal logic required for a universe to be coherent. The shock lies in seeing precision not as fortune, but as the shadow of a deeper, invisible simplicity. Fine-tuning grows more enigmatic when we explore what happens at the boundaries where universes fail. Most hypothetical universes collapse into triviality. No chemistry, no structure, no gradients, no time extended enough for complexity to accumulate. These are not barren worlds. They are worlds without the possibility of anything resembling a world. Shift the strong force slightly and nuclei never form. Shift the electron's charge and atoms cannot remain stable. Shift the cosmological constant in expansion either tears matter apart or crushes it instantly. The majority of parameter space does not produce different universes. It produces no coherent universe at all. The twist is that fine-tuning describes not a universe delicately shaped for life, but a universe delicately shaped for anything. This observation pushes the paradox beyond biology. Fine-tuning is not about accommodating carbon or cells, it's about enabling stable patterns that persist long enough to evolve. In most parameter combinations, matter behaves like an unstructured fog or collapses into uniform density. Without the narrow region where force is balanced just so, reality loses the ability to differentiate itself. No stars, no planets, no cycles, no memory, no direction for entropy to act upon. In such universes, complexity cannot emerge because complexity has nothing to anchor itself to. This leads to a profound shift in perspective. The constants we observe are not merely compatible with life, they are compatible with distinction itself, with the emergence of any phenomenon that can endure. They allow matter to separate, recombine, and store information across time. They create the scaffolding required for a universe to have history. In that sense, fine-tuning is less a biological puzzle and more a metaphysical one. Why does the universe occupy the narrow band where existence can accumulate patterns instead of dissolving into uniform noise? The shock comes from realizing that our cosmos is not one option among many. It is one of the few options where option has meaning at all. Fine-tuning becomes even more revealing when framed through information rather than matter. A universe capable of sustaining complexity must allow information to persist, propagate, and transform without immediate degradation. This requires an exquisite balance. Forces must be strong enough to create stable structures, yet not so strong that they freeze variation. Energy must flow in gradients gentle enough to support organization, yet not so weak that patterns cannot form. The constants of physics appear to define a narrow corridor where information can survive long enough to elaborate itself into atoms, molecules, cells, minds. The twist is that fine-tuning may not center on particles at all, but on the universe's ability to remember. Look at atomic structure. Electromagnetic strength determines how tightly electrons orbit nuclei. Too strong and atoms collapse into indistinguishable states. Too weak and electrons drift freely, unable to form stable chemical bonds. These bonds are not merely mechanical fixtures. They encode information about configuration and shape. Chemistry becomes a language and biology emerges from its grammar. Change the constants and the language evaporates. What fails is not life, but the universe's capacity to store distinctions. Thermodynamic considerations sharpen this further. Life exploits the delicate imbalance between order and disorder, extracting usable energy from environments where structure and randomness are both present. But these conditions require cosmic expansion to proceed at a rate that allows stars to form, planets to cool, and energy gradients to persist. If expansion races or stalls, entropy either homogenizes everything instantly or traps everything in static uniformity. Either way, the universe loses the intermediate zone where information processing becomes possible. This transforms fine-tuning into a question about the architecture of meaning itself. The constants define whether the universe can maintain patterns that evolve across time. And the shock lies in realizing that our cosmos balances on a line where information not only survives, it learns what it is. Fine-tuning reaches its most intimate scale when we follow its consequences all the way to consciousness. Every thought you experience, every memory, sensation, decision depends on physical laws holding their balance with microscopic discipline. Neurons fire because electrical potentials remain stable across membranes. Those potentials exist because electrons and ions obey quantized rules. Those rules depend on constants whose values cannot drift without erasing the chemical landscape beneath biology. Consciousness feels fluid and spontaneous, yet its possibility rests on numerical rigidity set at the universe's birth. The twist is that your inner world stands atop a scaffold of constants that had to be nearly perfect long before life began. Consider the energy scale of molecular interactions. Proteins fold reliably because thermal energies sit in the narrow range where bonds are neither so weak that structures unravel nor so strong that everything freezes into crystalline uniformity. This balance emerges from the interplay between electromagnetic strength and the masses of fundamental particles. Constants tuned so that chemistry hovers exactly between chaos and rigidity. Shift them, and biomolecules lose the flexibility that makes complex function possible. In most universes, the very idea of a living cell is mathematically excluded. Neural systems intensify this precision. Ion channels depend on delicate charge interactions. Synapses rely on molecular timing. Brain networks require long-term stability, yet constant dynamism. These conditions arise only because the constants governing diffusion, electrical interaction, and thermodynamic noise cooperate in a narrow window that allows signal propagation without destructive overamplification. Consciousness is not an emergent miracle floating above physics. It is the direct expression of a universe that allows sustained, self-referential patterns to exist. This convergence exposes a deeper implication. Fine-tuning is not merely the precondition for life, it is the precondition for awareness for the possibility of experience itself. And the shock comes from recognizing that the cosmos had to be exquisitely precise for anything in it to ever notice the precision. Fine-tuning begins to transform when we stop treating each constant as an isolated miracle and instead view them as expressions of a single underlying coherence. The paradox softens not by diminishing the precision, but by revealing how the precision threads through every scale of reality. Gravity, electromagnetism, quantum fields, thermodynamics, each law appears independent only when examined in isolation. But when seen as components of one interlocking architecture, their values behave less like improbable coincidences and more like coordinated constraints required for a universe that can unfold, differentiate, and sustain complexity. The twist is that fine-tuning might not be a collection of narrow accidents, but a single, deep mathematical necessity revealing itself through many parameters. Patterns emerge once we frame the constants as solutions to a shared set of boundary conditions. Physics often hides its simplicity behind layers of broken symmetry, where the rules appear arbitrary only because we observe them after the break. At higher energy scales, forces unify. At even deeper levels, space-time itself may dissolve into more fundamental entities, networks, relations, or algebraic structures, from which constants arise as stable eigenvalues. In that picture, fine-tuning does not mean someone set the knobs, it means the universe locked into the only configuration where self-consistent evolution is possible. Variation is not excluded by intention, but by mathematics. This integration reshapes the paradox entirely. Instead of imagining countless potential universes that fail, we see that most hypothetical configurations could never correspond to coherent law in the first place. They are not rejected realities, they are non-realizable states, like equations with no physical solution. The constants do not hover precariously on a cosmic razor's edge. They occupy the stable basin where existence can run its algorithms without collapsing. From this perspective, life and consciousness stop appearing as improbable beneficiaries of cosmic luck and instead emerge as natural consequences of a universe whose structure enables persistent, information-bearing patterns. The paradox then becomes a revelation. The conditions that allow minds to arise are the same conditions required for the universe to stabilize itself into a dynamic yet orderly whole. The shock comes from realizing that fine-tuning may not hide a purpose or a multiverse, but a profound unity. The possibility that everything coherent about the universe derives from the same silent mathematical foundation. Fine-tuning now appears not as an improbable arrangement, but as the signature of a universe that could not have been otherwise and still produce structure, memory, or awareness. The paradox resolves only when we understand that the constants are not curiosities floating above reality. They are reality's skeleton, the narrow grammar through which existence speaks. What once looked like an unlikely balance becomes the minimal framework required for a universe capable of unfolding rather than dissolving. The twist is that the mystery remains, but its shape has changed. Instead of asking why the constants allow life, we ask why coherence itself is possible. Seen through this lens, our existence is neither an accident nor a privileged necessity. It is a consequence of inhabiting a universe where information can persist long enough to refine itself into thought. The constants no longer seem tuned for us. They seem tuned for stability, transformation, and endurance, conditions under which life eventually becomes inevitable. The paradox softens not by removing the delicacy, but by recognizing that the delicacy arises from the very laws that make a universe real. And yet something quietly astonishing remains. We live in a cosmos where mathematics hardens into physics, physics blossoms into chemistry, chemistry deepens into biology, and biology awakens into consciousness capable of reflecting on the constants that made reflection possible. The circle closes in a way that feels both complete and impossible. You are the universe noticing the narrow margin that allowed it to notice anything at all. If you read this far, right, I exist because the constants hold.